Thank you very much. So indeed, this is going to be a two-part talk. I'm Peronnin from Alice and Bob. It's a pleasure to be here. So I'm here to discuss how at Alice and Bob we're leveraging the incredible hardware control electronics by quantum machine to build a universal fault-tolerant quantum computer. So this slide is going to be hard to decipher for you because of the lighting, but it's just throwing at you a few numbers about Alice and Bob. So Alice and Bob were a French startup building a quantum computer using a special kind of superconducting circuits, superconducting qubits. We use the so-called cat qubits. And those qubits are incredible because they offer a very straightforward path to fault tolerance. The company is about nearly 4 years old. We're 80 people. We've got most of our team in Paris, part of it in Boston. We raised $3 million in seed round and 27 in Series A. And the point of our technology, the cat qubits, is that they are autonomously correcting for errors. And actually, they're correcting for bit flips, one of the two kinds of errors. And so we believe we hold, by quite a bit, the world record for superconducting qubits in terms of bit flip times, with bit flip times that are often way above 10 seconds, with phase flip times that are about a few microseconds. So extremely noise bias for those of you who know what that means, meaning with the very asymmetric kinds of errors. And the whole point of Alice and Bob is to leverage this very peculiar kind of qubit to build a very straightforward path to fault-tolerant quantum computers. On the right here, mention one of our competitors, actually AWS, who's also building upon cat qubits and who just recently announced the first logical qubit. We're very excited about this coming publication. We're also live on a few platforms. We announced our partnership with Equinix to distribute this computing power. We'll soon announce one of the big hyperscaler. And we do a bit of consulting like any serious quantum startup, I guess. So just a few words about the technology and the promises and where we are at in terms of technology when it comes to building a quantum fault-tolerant quantum computer. So the first line is about building a so-called semi-logical qubit. What does that mean? It's a kind of a made-up word to mean that we're correcting half of the errors. And here we're comparing two papers, one by Google, published in Nature earlier this year, and our latest paper about cat qubits. And so in the latest Nature paper by Google, where they demonstrate error correction just at threshold for the surface code, they also mentioned that they can use the whole Sycamore chip as a big repetition code and manage to correct errors, bit flips, for about 6 orders of magnitude, if my memories are correct, which is exactly the kind of performances we get with our single cat qubit just by turning it on and letting it operate. So this is how hardware efficient the approach is. Another point I love to make is about the architecture, the big picture kind of scheme. Here again, comparing two papers, one attributed by us to Google because it's a Craig Gidney's paper actually, where he demonstrated that to break RSA 2048, which is a great benchmark for architecture, they would require about 20 million transmon or standard superconducting qubits. We slashed these numbers by 60-fold, meaning we got rid about 98% of the qubit requirement, down to about 350,000 cat qubits required with the same level of hardware hypothesis. And the reason behind that is exactly this point of having this autonomous built-in error correction hardwired directly in the chip. But to put those numbers in perspective and to tease you a bit with what's coming up next for us, when you think about those 20 million required qubits, actually out of those, only 0.03% actually compute or are required by the algorithm. Shor algorithm to break RSA 2048 requires about 6,600 something qubit to operate. So that means that 99.97% of the qubits are just overhead. So in some sense, one could argue that in this architecture, a quantum computer is actually a machine that does not compute, but corrects its errors, and from time to time happen to compute. We make these numbers 60 times better to about 2%, which is already incredibly better. And the idea is really that we gain a square root ratio on this overhead, on this 0.03%. And this square root ratio, where does it come from? Well, pretty simple when you think about it. A surefast code has 2 dimensions because you have 2 types of errors. In our approach, we natively suppress one of the 2 types of errors, so we only need a repetition code. So 2%, great, but we're not done yet. We'll soon announce a much better architecture, getting this at least a few fold better by the end of January, just teasing you. And in terms of hardware development, where we are at, we're currently operating a 4 cat qubit device, and we'll very soon announce Helium-1 16 cat qubit device that during next year, once calibrated, will be a proper logical qubit in some sense. There we go. So as a challenge to operate our devices, well, you find all the usual challenges of superconducting qubits. And the reason why we went with a quantum machine is because we need a very flexible API. In this age of quantum computing, all the instruction set of the machine are not completely settled. So we're really looking still for FPGA boards where we have this flexibility to fine-tune the pulses, operate the machine in the most optimal way. The frequency range are in the order of between 2 and 10 gigahertz, and we need some very fine quality. And all those are great features of the quantum machines devices. Finally, something I haven't mentioned is that superconducting cat qubits would have a footprint just the same as your usual transport or standard superconducting qubits. You can see a snapshot on the bottom left here. They also have gates that are just as fast, meaning single qubit gates takes a few tenths, about 20 nanoseconds, and 2 qubit gates are about 100 nanoseconds. So we need very fast pulses to operate this. And we want it to build in a very seamless software integration to take into account the error correction code, the decoding of the syndromes, and all this have us think about the whole stack. And I guess this is why we partner with Quantum Machine, because of their great hardware to develop that. And without further ado, I would invite my colleague, Yonatan, to tell you about quantum machines.
Let me say that I'm very, very excited to give this unique talk together with Theo and Alice and Bob. For us at Quantum Machines, we're not building the full stack quantum computer. We're providing systems and supporting others who are building the full stack quantum computers, like Alice and Bob. So for us and for me personally, this is the best part of the job, is to see our customers and our partners actually succeeding in doing so. So it's really great to give this talk together. So we're making the classical part of the quantum computer. As Theo mentioned, the control electronics, that is the classical electronics that connects to the quantum processor and operates it using high-frequency signals, as Theo just explained. At Quantum Machines, we've developed a platform called the OPX platform that has unique technology inside of it. It has what we call the pulse processing unit. That is the classical processor. It's not a quantum processor. It's a classical processor that communicates with the quantum processor, basically generates all these pulse sequences, fast signals that go to the QPU and operate the QPU. And we've developed a programming language that we call Qua. That's a very kind of intuitive way to program the pulse processor and in turn to program the quantum processor. So for us, this is kind of a change of paradigm from what we call a memory-based approach to quantum control to what we call a processor-based approach to quantum control. In a memory-based approach, Traditionally, what people used to do is they used to take, to generate all the signals you want to send to your quantum processor in software and then load them into a big piece of memory and then just hit a play button like an iPod, and then you play all the signals to your quantum processor. That's the memory-based approach. The pulse processing approach is where you actually have a processor inside the control system, and it generates the signals that you send to the QPU by itself on the fly in real time. I don't have time to tell you about why this is an important technology, but I can tell you that this is the reason for why we were quite successful in the market with over 250 customers by now around the world, over 160 people at Quantum Machines employees, and we were also selected by the Israeli government to build the Israeli Quantum Computing Center in Israel. And so one example for the use of the pulse processing unit is by Alice and Bob. This is how they, well, one example of how they're using it. This is a typical measurement, a typical characterization that one performs on these cat qubits, this very unique type of qubits that Alice and Bob is working on. And typically, just to do this characterization with this memory-based approach takes a long time. With the pulse processing unit, because it generates all these signals on the fly in real time, you can get sometimes orders of magnitude speed up in how fast you, even just characterizing your qubits, not to mention more complex algorithms. So that's an example for that. And now we're taking our next step from basically creating controllers for R&D to what we call a quantum data center ready quantum control system. We recently announced the OPX1000. This is our new quantum control platform that is a massively scaled up system with the highest channel density that's available today in the market. That's the channels that actually drive the quantum processor. You want as many of them in a single unit rack so that you can build a relatively compact quantum computer. And you can stack many of these together to control hopefully hundreds and thousands of qubits. It's got the real-time pulse processor that I mentioned. It's got state-of-the-art analog specifications. As Theo mentioned, this is what's needed in order to push fidelities to the limit, and this system is actually pushing some of the analog specifications and the gate fidelities to the limit. And finally, data center ready, which means this system's got all kinds of hot swappable components and monitoring and redundancy that will allow us to be available for users. Okay, so we're very excited to be working with Alice and Bob. For us, it's more than just providing our control systems to Alice and Bob. It's really working with Alice and Bob on a day-to-day basis, understanding not just how do we meet those challenges. This is a heavy slide, I know it's got a lot of, but the message here is that we don't just walk and work together to meet the current requirements, but also thinking about roadmaps in the future. Quantum computers are not going to look like what they do today in 5 years from now. And this partnership is really about pushing the limits of what will be possible with quantum hardware. So today we're kind of trying to meet all these challenges that Theo mentioned, like the flexible APIs with our programming languages, the high frequencies, the signal quality, the nanosecond scale latencies, and so on. But for us, it's really how do we work together and building towards quantum error correction. Yeah, so I think this is our story, our mutual story of working together. We strongly believe in what Alice and Bob are doing. This is hardware efficient quantum computer is very, very important for us to kind of accelerate the timeline towards a fault-tolerant quantum computer that could run applications. Yeah, and we thought to have a little bit of time also for questions, so I think we can do that now. Thank you. This is extremely, the light is extremely in the face, so I'm not seeing exactly, I think, yeah.
David Shaw, Global Quantum Intelligence. Some of the other the tech major developers of quantum machines have emphasized the cryo electronics that they're developing for control. what's the quantum machines approach to what temperature you control electronics is going to run at?
Yeah, that's a great question. So we're doing research on the subject. Currently, in the current systems that we have and in the systems that we will have in the next, I would say, 2 to 3 years, we don't see an immediate need to go to cryoelectronics. But after that, probably beyond 1,000, if we're talking about superconducting qubits, probably beyond 1,000 qubits, you already need some cryo components. I wouldn't say you need the entire control system to go down to low temperature. There's some thoughts about this, but we don't see it as the right path. Like, frankly, like this would, in my opinion, to really make cryoelectronic chips that bring the system that you saw, all the logic that you saw in this box that I just showed, down to cold temperature. That's a 10 or 15-year project by itself, and probably not even necessary. But there will be certain components like cryomultiplexers and voltage sources, DC voltage sources, things like that that would probably be needed beyond 1,000 superconducting qubits. So yeah.